This is ELC 131, Circuit Analysis 1, and this presentation is on parallel RLC circuits. So Figure 1 shows us an example of a parallel RLC circuit. And in parallel circuits, the voltage is the same for all components, both in magnitude and time. So V source equals VC equals VL equals VR. So we're going to use voltage as the reference for this circuit with respect to time. And we see this illustrated in Figure 2. The sine wave that describes the source voltage begins at 0 volts at 0 degrees. Now, there's no difference in time between when voltage is applied to and current flows through a resistive element. So IR and VS are in phase with each other, as shown in Figure 3. But from our previous discussions of the action or operation of capacitors, we recall that current leads voltage by 90 degrees in a capacitor. Therefore, the capacitor current happens 90 degrees before the resistive current, as shown in Figure 4. And in an inductor, voltage leads current by 90 degrees, so the inductor voltage happens 90 degrees after the resistive current, as shown in Figure 4. Now we illustrate this phase relationship with the branch currents in that parallel RLC circuit with a vector diagram as provided in Figure 5. The resistive current and source voltage are our reference quantities, and they're plotted or placed at 0 degrees on the vector diagram. Since the capacitive current is 90 degrees ahead of the resistive current, IC is placed at positive 90 degrees, and IL is placed at negative 90 degrees, since it happens 90 degrees after the resistive current. And referring to the vector diagram of Figure 5, note that IC and IL are 180 degrees apart. And this is illustrated further in Figure 6, that IC and IL are flowing in opposite directions. When current flows down through the capacitor, current flows up through the inductor, and vice versa if current's flowing up through the capacitor, current's flowing down through the inductor. Now, the source current, as described by Kirchhoff's current law, is the sum of IC, IL, and IR, but since these currents don't happen at the same time, we must combine them as vector quantities. So the source current is equal to the square root of IR squared plus IC minus IL squared. And we can calculate the phase angle of the current, the source current in the circuit, by finding the inverse tangent of IC minus IL over IR. And again, note, if in this equation, if IL is greater than IC, then we will return a negative value for theta. Now let's look at the calculations of the currents in the circuit of Figure 1. So Figure 1 shows us a 1 kilohertz sinusoidal source with a peak value of 14.14 volts. And this is connected to the parallel combination of a 1 microfarad capacitor, a 100 millihenry inductor, and a 100 ohm resistor. So our calculations have to begin with calculating inductive reactance and capacitive reactance. Inductive reactance equals 2 pi FL for the circuit of Figure 1. it is 628 ohms. And capacitive reactance is 1 over 2 pi FC. For the circuit of figure 1, it is 159 ohms. So the current that flows through the inductor, Vs divided by X sub L, is 15.9 milliamps. The current that flows through the capacitor, Vs divided by X sub C, is 62.9 milliamps. And the current that flows through the resistor is Vs divided by R. 10 volts divided by 100 ohms gives us 100 milliamps. Now all these values for the branch currents are RMS quantities. I have converted the 14.14 volts peak to its RMS equivalent of 10 volts. So the current supplied by the source, again, is the vector sum of IR, IC, and IL, which equals the square root of IR squared plus the difference between IC and IL squared, which for figure 1 is 110 milliamps. Now the phase angle between the source current and the source voltage in the circuit of figure 1 can be calculated with the equation shown, the inverse tangent of IC minus IL, which gives us a phase angle of 25.2 degrees. So this is the phase angle between I source and IR, which is also the phase angle between I source and V source. Now we can calculate the impedance of the circuit of figure 1 using Ohm's law, where Z equals V source divided by I source. So the impedance of the circuit of figure 1 is 90.9 ohms. Now the impedance can also be calculated using the reciprocal formula as shown. However, with the parallel RLC circuit, we cannot use the product over sum equation to calculate impedance. And this is the same as with a purely resistive circuit that has 3 resistors in parallel. We cannot use the product over sum equation to find the total resistance.